All right, great. Let's move on. So the next talk is by Rahul Krishnan from University of Wisconsin-Madison, who will be telling us how to speed up synthesis by using monotonicity. The floor is yours.
Oh, perfect. Okay, thank you. Thank you for the introduction. Hello, everyone. Thanks for coming to my talk. So I'm Rahul. I'm a PhD student at the University of Wisconsin-Madison, and I'd like to tell you about our work on how we can automate the construction of pruning approaches in top-down enumeration based on proving a semantic property of monotonicity. So I'd first like to discuss the pipeline of how domain-specific synthesizers are typically developed. So first, you would define a synthesis problem, which is typically defined as a behavioral specification and a search space. For this work, we're mostly going to focus on when the behavioral specification is a set of input-output examples, and our search space is defined as a regular tree grammar. Then, typically, a domain expert would step in and construct a bunch of manual observations whose insights will then be used to inform a synthesis algorithm that is manually constructed. And so the problem here is that these observations have to be manually constructed, and therefore this algorithm manually developed for each domain. So the goal of our work is to automate this process for a large number of domains. So a very simple but effective strategy for synthesis is that of top-down enumeration. The idea is that you'd start with you would enumerate programs in increasing size of, let's say, of the size of the abstract syntax tree until you find a program that satisfies your behavioral specification. The problem is such an algorithm, when done naively, leads to an exponential blow-up. And so a traditional way to solve this problem is to consider templates like the one we have here, where a template is an abstract syntax tree that contains a hole, that's that square thing, that represents an empty context that can be instantiated with any derivable term from that non-terminal. And so notice that a template represents a set of programs. And the set of programs in this diagram here that is part of that template, I've highlighted in yellow. And so the idea is that if we can somehow prove that this template cannot satisfy our behavioral specification, meaning that no derivable program can satisfy, no derivable program from this template satisfies all of our behavioral constraints, then what we can do is then prune that template, which then lets us prune this entire set of provably incorrect programs. And so notice that this set is potentially infinite. And so what we're able to do is we're able to guide our synthesizer away from provably incorrect programs and towards more likely ones. So top-down enumeration has actually seen success in a lot of domains, such as regular expressions, imperative programs, SQL queries, and data log programs. And the key to scaling all of these approaches, we're coming up with this sort of pruning approaches via coming up with domain-specific observations. So let's actually look at a couple of example domains. On the left, we're going to be considering the pruning approaches for regular expressions. And on the right, we'll be considering the pruning approaches for imperative programs. So a tool like AlphaRegX is a synthesizer for synthesizes regular expressions. And we'll try to we'll consider these templates in order to try to prune these templates away. And the way a tool like AlphaRegX would approach this is by constructing upper and lower bounds on the language of this regular expression. So we can construct a lower bound by replacing that hole with the least permissive regular expression, and construct an upper bound by replacing it with the most permissive regular expression. And then if we know that if any of the behavioral constraints fall outside of these bounds, we can prune this template away. A similar process can be done in the imperative case, where a tool like Simple will construct a range of values for the outputs of the variables in our program. So in this case, just as an example, we'll see that no matter what we instantiate our hole with, x will always be bound. The output of x will always be bounded by 0, since it'll never change, and y is unbounded, so it can be any integer between minus infinity and infinity. And if we know that any of our behavioral constraints fall outside of these intervals, then we can prune this candidate away. So what we're going to show, what we showed in our work, is that while these approaches seem different and were the major contributions of these individual papers, we show that these can actually be reasoned about in exactly the same way. And the way we're going to do that is by constructing interval abstractions that over-approximate the set of possible values that these templates can take on. And so notice that the observations these domain-specific tools made actually end up matching the intervals that we generate. And so the main contribution of our work is that we're able to unify these approaches under a single umbrella of interval-based abstractions. So let's actually discuss how we generate these intervals. So let's reconsider the ASTs from before. We're going to start by generating intervals for the leaves and construct abstract transformers to generate intervals for the whole AST. So the 0 is a concrete value, so we know it can be over-approximated by the singleton interval 0, 0. And for now, we're going to replace our whole with the widest possible interval, or top. So in this case, our interval is going to be from the least permissive regular expression to the most permissive regular expression. And then I claim that a sound interval transformer for this concatenation operator is simply just applying the concatenation operator to the left and right bounds of our of its children. And so I've colored the left bounds in purple and the right bounds in blue to show this. And a similar process can actually be done in the imperative case, where again we construct intervals for the leaves, we propagate these intervals up, specifically by constructing these interval transformers by applying the concrete semantics of each of these terms to each of the endpoints. And so these intervals are sound for the examples I've shown, but they may not always be. And so in order to automate this process, we may ask, when is this actually possible? So let's look again at our concatenation operator to gain some intuition. The concatenation has this really nice property that if, let's say you take two regular expressions, R1 and R2, if we know that the language of R1 is a subset of the language of R2, then if we take a third regular expression, R prime, then we know that the language of R1 concatenated with this third R prime is a subset of R2 concatenated with R prime. And this is true even if we swap the order of concatenation. And so this gives us intuition for our notion of monotonicity, which is that we say, suppose we can prove our concrete semantics, F, is monotonic on each argument with respect to some order, where monotonicity in this case is just the standard definition of monotonicity. Then we can get the abstract transformers, this F-sharp thing, simply by applying this endpoint recipe that I talked about, where we take the intervals as inputs and apply our concrete transformer F on the left bounds and the right bounds respectively. So to connect this with our example above, in the case of regular expressions, our order here was just language inclusion. And what's nice is that the abstract transformer that we get here was effectively acquired for free given a proof of monotonicity. So these interval semantics have some nice properties. The first is that they're sound. We showed in our work that these are sound, in the sense that for any template, the interval that we construct will cover the set of possible outputs that any derivable program could output. It's also precise, in the sense that for it's the tightest possible interval that is also sound. And finally, we show that this process can actually be fully automated. So I mentioned in the previous slide that given a proof of monotonicity, we can generate our intervals pretty easily. But we show in our work that we can actually, given the concrete semantics of the terms in our language, we can query an SMT solver for proofs of monotonicity, and therefore fully automating this entire process. And so this is the monotonicity is the sufficient condition to generate these intervals and rationally reconstruct the approaches we saw in domain-specific prior work. So we generated these precise interval transformers for operators that could be proven to be monotonic. But we actually found one other way that we can make our interval abstractions for the whole abstract syntax tree even more precise. And so that comes from the observation, this comes from something I said earlier in the talk, which is that currently we set the interval for this whole to be the largest possible interval top. We just sort of defaulted to that. But there's this question of what if we can learn more things from the grammar? So as a very simple and restricted case, consider this non-terminal where we take E and it just goes to the number 0, 1, or it can recursively add two terms together. Like I said before, we currently default this interval we currently default the interval for this hole to be the interval minus infinity to infinity. But if we look at the structure of the grammar and the semantics of addition, a sound interval that would work is simply just the interval that covers all non-negative integers, 0 to infinity. So what we can do is we can actually replace our old interval of top with this new one, and then propagate this interval upwards until we reach an interval for the entire abstract syntax tree that is now even more precise than the one we generated before. And so the way that we would generate this interval is we use a technique called grammar flow analysis. It's an iterative approach where we can start with our interval top and iteratively query for tighter and tighter bounds until we reach an interval that is precise for that non-terminal. So I don't, unfortunately, have time to go into the details of how our grammar flow analysis technique actually works in detail, but please check out the paper if you're interested in more details. But we show that this process can also be automated by an SMT solver. So in this way, we're able to fully automate the construction of these intervals for these holes, as well as these abstract transformers for all of the recursive terms. So both the monotonicity checks and our grammar flow analysis required reasoning directly about the semantics in order to generate these interval over approximations. And really, the ability to directly reason over the semantics is what the SEMGIS framework gives us and is what actually enables our entire technique. So for background, the semantics guided synthesis, or the SEMGIS framework, is a domain agnostic framework that allows a user to supply their own semantics to the terms of the language. So before I said this synthesis was defined, the synthesis problem was defined over a search space and a behavioral constraint. But now there's this third element of the semantics that can be given as input to the synthesizer. And this user-defined semantics is actually what is unique to the SEMGIS framework. So now, given the semantics, we can actually then apply the techniques that I've talked about in this talk to then encode whether a semantics is monotonic and perform grammar flow analysis, the whole process which can be automated using an SMT solver. So for our evaluation, we tested our framework by building a synthesizer that takes in benchmarks from the SEMGIS framework and generates the abstract intervals that I've described in this talk. And so we evaluated on a number of benchmarks from a number of domains, and we wanted to, we wanted to compare the performance of our tool. And so in this first graph, we wanted to evaluate the performance. So in this case, the way you would read this is down and to the right is better, as that indicates that tool is faster on more benchmarks. And what we see is that the brown line, which I guess is very close to the black line, which is so the brown line is our tool that generates that performs pruning, that uses the intervals from both the monotonicity proofs and the grammar flow analysis. That outperforms both the baseline, which is just a naive enumeration that doesn't have any pruning. That's the blue line, as well as our ablation, where we only generate intervals using just the monotonicity proofs, but not our grammar flow analysis technique. We also wanted to see how effective it was at searching farther in the search space. So this graph is on benchmarks that the tools were not able to solve. And so in this case, actually up and to the left is better, as that indicates that that tool was able to search much farther in the search space. And what we see is, again, that brown line outperforms both our ablation and the baseline naive enumeration. OK, so in conclusion, we started with this pipeline for the domain-specific solvers, and we replaced the domain expert with this new pipeline that is able to automate the process for a large number of domains. And so to recap, we start with the synthesis problem that is defined in the SEMGIS framework. I unfortunately didn't have time to talk about this in my talk, but for the definition of monotonicity work, it inherently requires an order. We have a way to find a good order to use for these monotonicity proofs. We then run an analysis that involves generating monotonicity proofs and grammar flow analysis based on the semantics, and we show how this can be fully automated by an SMT solver. And this analysis can then be used to generate interval semantics that we've seen can rationally reconstruct prior interval approaches in domain-specific tools. We can then feed these intervals to an enumerative solver that allows one to then prune partial programs, which we have shown in our evaluation allows us to synthesize solutions faster as a result of these pruning approaches. So we think this opens the door to a lot of future work. The first is that the order that you use to generate your intervals can actually lead to different types of intervals being generated. So how do we sort of leverage different orders and different intervals for better pruning? We focused entirely just on the interval abstract domain, but are there other abstract domains that we can automatically come up with by analyzing the semantics and that we can use for pruning? And finally, we focused entirely on top-down enumeration. But is it possible to perform this kind of reasoning on other type of synthesis algorithms as well? So SemGIS solvers are still in their infancy. So we hope that ours can be the first in a series of improved solvers that are able to leverage analyzing the semantics in order to improve the performance of synthesizers. And so with that, I'd like to say thanks again for coming to my talk.
Thanks for the very nice talk. We have time for questions. First you, then others.
Hello, very nice talk. So I'd like 2 questions. So first one is that when you say you have to apply the abstract transformers, you have to define the abstract transformer for each operation in your grammar?
So the abstract transformer that's the interval construction I was talking about from the monotonicity proofs.
For addition, you have to do add. For subtraction, you have to minus. So for each operation in grammar, you have to give abstract transformer differently, or you generate automatically?
We generate it for each term in the grammar.
Okay,
yeah.
Sure. So the second question is like when you said that you have compared with your baseline for the SemGIS.
Yes.
So have you tried with your optimization for the same domain? Like if you have have you tried with your timing with SemGIS and the sketch for the for same kind of domain? Have you tried different solvers, synthesizers engine with your tool? Because you compared with your baseline SemGIS, but
yes,
for different domains there are different synthesis engines.
Right, right.
So have you done this comparison, like what sketch that's in how many, or CBC5?
So we did not. So the reason is that the SemGIS framework is much more general than these.
Yeah, I agree.
But
I agree. I'm not comparing for different domain.
Okay.
Fix the domain. For that particular domain, what's your comment on? Will it be better or worse?
You're saying, sorry, just to clarify your question, are you asking whether, how we would compare our solver against something like Sketch, which,
yes.
Okay, yeah. So we did not perform that comparison, but our set of benchmarks, if we tried to compare against Sketch, there are a lot of benchmarks in our problem set that Sketch would not be able to solve, just because of the generality of the SemGIS framework, and so we weren't able to perform a direct comparison that way. Oh, sure, yeah.
All right.
Hey, I was just curious. So this looks very similar to Morpheus to me, in that it seems like it's essentially a very similar algorithm, but just customized to the interval domain. I'm just curious if I'm missing something, or maybe could you I guess compare and contrast to that work if you know it?
So I'm unfortunately not familiar with Morpheus. Yeah, maybe Loris can talk about it.
So I think the short answer, I think in Morpheus, you have picked a domain for which you figure out how to do synthesis of transformers. This is the dual of it. We picked a domain for which you do not have to synthesize transformers. Transformers are for free. What you have to figure out is when the transformers can be synthesized for free. And so the idea is that there is actually this paper we found out about a week ago at POPL this year, where they started to do the similar observation for abstract interpretation in general, that basically monotonicity is what tells you intervals are great. And so there they use it for verification. Here we use it for synthesis, as in, if you're monotonic, then you get these transformers for free. And so that's the big observation of the paper, versus in Morpheus, it was like, here is one domain that works well, here is how we synthesize for it. And so it's kind of related but different, yeah.
All right, let's take the rest offline, and let's thank the speaker again.